Today we're going to be talking about linearization and differentials. So we're going to consider this equation. We're going to graph that equation in y1 on your calculator. And eventually we're going to zoom in at the point x equals 1. I also want us to find the equation of the tangent line at that point x equals 1. So the equation of the tangent line, we need the point that's on the line. So 1, when I plug in 1 into this equation, I get 1 as an output. Now we need our derivative. The derivative of that is 2x. The derivative evaluated at 1 is equal to 2. So the equation of our tangent line is that I'm going to solve for y so that it's easiest for us to plug into our calculator. I'm not going to simplify. In y2, I want you to put that equation. And let's zoom in at the point x equals 1. And I'm going to do that next in the video. And there's an important concept that I want you guys to realize. Okay, so in y1, I've asked you to graph the equation that I gave you, y equals x squared, and then the equation of the tangent line. Now, when I press graph, we get that graph. But I want to zoom in around x equals 1. So I'm going to get my cursor close to 1, so trace 1 so that it's close to it. Then I'm going to do a zoom in on that point, zoom 2, and press enter. And I'm going to keep doing that. Trace. Oh, I can't trace yet. My calculator is slow, I apologize. Trace 1, enter. Zoom 2, enter. Now look what keeps happening to my quadratic. Remember, quadratics were a parabola shape. Notice how this line is getting really, really close to what we have our tangent line, but our parabola is even starting to look like a tangent line. If I zoom in again, trace at 1, press enter, zoom 2, press enter again. Now that even looks like our line. And look how close our tangent line is to our actual curve. So that's kind of the point. When we zoom in really, really close, this is really, really close to 1. Say I wanted to zoom in again, just for fun. And while it's graphing, look how close this looks to a line. And look how close our tangent line is. It's almost like they're one's on top of the other. So that's the point of this lesson, is for you to understand that when I zoom in really close to an x value of any type of function, zoom in infinitely close, your tangent line and your curve are almost identical. So we can use our tangent line to approximate what our actual curve values could be. And that's one of the cool things that I think about calculus. Okay, so we zoomed in, and notice how this is a different way of looking at it. We have our graph, and we have our point, and again, our tangent line approximates values of this quadratic. When we zoomed in on this quadratic, it was practically linear here as we were really, really close to 1. One of the things we're going to be doing is we're going to be looking at this point 1.2 and approximating the tangent line at 1.2. So what was our tangent line approximation? Well, the tangent line approximation was real close to our function value. You could actually use your tangent line and plug in 1.2 for x to get the actual approximation. And that is the whole goal of today's lesson. Okay, so now the calculus behind everything. So f is differentiable at the point, and we have our equation of our tangent line. Okay, that's why back here on this slide, that's what I have there. F prime at A or a, and this was f of a. So our linear approximation is this. It's a linear approximation of an actual function. Okay, and that's called the linearization of our function at a, because when we zoomed in real close, our quadratic almost looked like a line. So that our function value can be approximated by this line, where a is called the center of approximation. Now let's talk about over approximation and under approximation. Over approximation all has to deal with concavity. When we are concave down, say there is our point of tangency we're using to approximate. There's my tangent line. There's my tangent line. Is this point, either side of my point of tangency, say let's go over point 2 or whatever, delta x. Is this point that's on my tangent line an over or under approximation of my actual function? It's above, so it's an over. So we over approximate when we are concave down. It doesn't matter whether you're increasing or decreasing. Okay, here I was increasing, here I'm decreasing. That's the point I'm trying to approximate. My tangent line's actually going to give me that one. That's an over approximation. So now we have our functions when we are concave up. Doesn't matter whether I'm increasing or decreasing. So we have this point here, that point there, okay, that we're going to approximate. There's our tangent line. There's my tangent line. Now, this point up here, I'm trying to approximate that. My tangent line's actually, the actual y value of my tangent line's below. It's an under approximation. Here, I'm trying to approximate this value. My actual value is greater than, so my tangent line is an under approximation. It is less than what the actual value is, and this is when I am concave up. So over approximation, under approximation deals with concavity. That is super important for you to remember. Okay, example 1. Find the tangent line approximation. Basically, you're finding the equation of the tangent line at the point 2,8. Use that tangent line to approximate my value of 2.1. Determine whether we are an over or an under approximation. So let's first find our derivative. I feel like I was talking really loud. I apologize. So our derivative is 3x squared. My derivative evaluated at the x coordinate of 2 is going to be equal to 12. So my equation of my tangent line is y minus 8 is equal to my slope, which was 12, x minus 2. I'm not going to simplify, but I'm going to add that 8 over, because this is our approximation of our function values around this point, x equals 2. Actually, I should have little approximating symbols in there. So y now is approximately, for this function value, is approximately, plug in this as your x. 2.1 minus 2 plus 8. Doing all of the algebra on there. I'm not going to bore you guys with algebra because it's boring. I love algebra. Not going to lie, I love algebra, but you guys don't need me to do the algebra there. Okay, this is approximately 9.2. So now we need to determine, is it an over approximation or an under approximation? Your justification for this, I'm going to ask you guys to justify it. Yeah, you could actually plug in the value and get what 2.1 is to the third power. But that's not using calculus. That's not utilizing the skills that we need. Let's find our derivative. Let's use the calculus. 6x our derivative evaluated at 2 is 12 again. I'm sorry. I was looking at that and I was like, that's kind of fun. So our second derivative at 2 is greater than 0, so we are concave up. When we are concave up, that is an under approximation. Now, let's actually find the value. You would normally not do this part, but let's find f of 2, which that ends up being 9.261. My actual value, this is greater than this value, so that's why this value is an under approximation. Everything in black here, everything that I have that's not in this little box area, is the calculus that you would need to justify. For this example, we're going to find the linearization of our function at pi over 2 and use the linearization, not it. I'm sorry, I apologize. I always yell at you guys about using the word it. Use the linearization to approximate cosine of 1.75 without a calculator. Is this an over or under approximation? Quite honestly, I would give you an example more similar to the previous one, where it's going to be easier decimals. We don't know what pi over 2 is without doing a little bit of work to get what pi over 2 is as a decimal to 3 decimal places. So let's take out this without a calculator piece, and let's use calculus to justify our answer, but we're going to have our calculators to help us out. So our first derivative of this, which is our first step we find, is the negative sine of x. So then we find f prime at pi over 2. The sine at pi over 2 is -1. So then we write our linearization. This is better notation than I had on the last slide, which is approximately our slope, x minus pi over 2, plus our y-coordinate for our function f of pi over 2 is equal to 0. So I don't have to worry about adding anything. So this is our linear approximation. Now what all I have to do is plug in, this is approximately, -1, 1.75 minus pi over 2 minus pi over 2, and that's approximately -0.179. Now let's look and see whether this is an over or under approximation. And this is actually a really fun example for this. So we look at our second derivative, which is the negative cosine of x. So we look at the sine at pi over 2 of this negative cosine of x. We all know, hopefully, cosine of pi over 2 is 0. Wait! 0. What do I do if it's 0? 0 is neither concave up nor concave down. And this got me, so I had to re-record it. And I had to think about it. Let's look at 1.75. Let's look at the sine at 1.75. So the second derivative at 1.75 is actually greater than 0, which means we're concave up. So therefore then this is an under approximation. So this -0.179 is an under approximation. When I actually evaluate the function at 1.75, that is equal to -0.178. And now notice how this number is a little bit bigger than this one, so this is less than, that's why it is an under approximation of my actual value. Okay, that's it for today. Please make sure your lesson summary is submitted on time.